All right, guys. Who is here for extra credit for a class? Who is here for their MMII certificate? Then I won't even talk about it. So tonight's presentation is a curious history of mathematics. So I'm assuming everybody's in either statistics or math class, correct? Not here because you like history. This is Professor John Oakes. He's one of the instructors here at Home Community College. Excellent on the topic of statistics and mathematics. And without further ado, we're going to have a discussion on this wonderful book. If you want to read it, we have copies here. You can check them out. So feel free to take one. Check out the library at the end of the presentation day. Okay.
Thank you. By the way, you're in one of my classes. I think that some of you did not double check the brochure to make sure that you had the right time. So just make sure that you fill out the survey as we go and give it to me at the end, and then I'll make sure that you get an extra special bonus for actually being here at the live presentation. Did anyone read the book by any chance, though? No, that's not true. But anyway, this is a book that talks about see, now the slide doesn't even advance. This is not good. I wonder if that's why it's. See how it works. So this is a book that actually starts by going through the beginnings of mathematics and then walks you through the classical era, ancient Greece era, medieval era, Renaissance, and the Revolutionary era, and then into the modern era. So there's 6 questions on your questionnaire, and we'll sort of use that as the outline of what we're going to talk about tonight for the next hour. So I'll probably talk about an hour or so, and then after that, let you ask any other questions or go ahead and finish your survey or whatever you feel the need to do. So I'm going to stop along the way and ask you if you know who some of the famous mathematicians are that I'm going to show you, and if you happen to know, I'll give you a prize. So, okay, does anyone happen to know who this guy is? Or can you even see him? I can barely see him, but does anyone know who he is? Does anyone want to make a guess? Maybe. I feel like you can, yeah, somebody who did math. That's a very good guess. So, no prize or anything for that, sir, but a nice guess. So, I will say that this guy is Gauss. Yeah, see, now you know that. Why didn't you say something sooner?
Let's figure it out.
Oh, yeah. Oh, yeah, this guy happens to be Gauss. And do you happen to know what Gauss was famous for? I'll give you a prize just for knowing who Gauss is, but you happen to know what he was famous for? Yeah. So he actually had over 100 theorems or different procedures named after him. So over 100 different theorems or procedures in mathematics were named after this man, Gauss. And this was a guy who was born in 1777, so he lived until the 1800s, and he was from Germany, but because of all these theories and things like that he came up with, that's why a lot of people call him the father of mathematics. Right? So there's lots of fathers of mathematics, depending on who you ask and what country you ask, but this is one of the guys. So one of the things that he is really famous for, besides the Gauss-Jordan elimination, is for this problem right here. So does anyone know what the answer is when you add all the numbers from 1 to 100 together quickly? So if anyone can tell me in 5 seconds, I'll give you a prize. Yes, go ahead.
5,050.
No, not even close.
Wait.
Yeah, okay, so it was 5,050, but how did you get that?
It's n times n plus 1 divided by 2.
Yeah, all right. So that is one of his famous actual theorems that he came up with. And so Gauss's shortcut to doing this was coming up with the formula was exactly this. He added the 1 and the 100 together, and then he added the 2 and the 99 together, and then the 3 and the 98 together. Each of the times you do that, you get 101. And so you do that 50 times, and 50 times 101 happens to be 5,050. So who has heard of that shortcut before now that you've seen it? Yeah, I mean, I do think it's a popular shortcut once you have seen it, but if you haven't seen it before, then it could be a little bit harder to figure this out. Right. So you could generalize this, and if you want to sum up all the numbers or add up all the numbers from 1 to 100, then I know it is 50 times 101, but I could rewrite it as 100 over 2 times 100 plus 1, and then that 100 could be any number, so it's the number that's the highest number you want to add together, divided by 2 times that number plus 1. So that's the easiest way to get that formula, but I do feel like this says a lot that Gauss went from just one simple case that he was asked to do of adding up numbers 1 through 100, but then all of a sudden he came up with a general formula that could be used to add up all the numbers from 1 to 200 or 1 to 300 or 1 to 400 or whatever you want to add. Yeah. So I think he was an interesting man. And actually, if you read the book, you'll find out that a lot of the people in this book died from random things. Like one of the guys we'll talk about later, he died because his wife actually said that if you die from a cold, then it was because you were cold. So what she did was when he got sick with a cold, she said, well, the way to get rid of a cold is to throw a bucket of ice on you and make you colder, because the cold will make the cold go away, and actually it did the reverse. So these people back in the day, they were great mathematicians, but they had zero life skills, and you can read the rest of the book, but I do think it's interesting that happened. And then another guy that we'll talk about later on, he died of pancreatic cancer, and it was like right before he invented an entire bus system. So I mean, very interesting guys. Like on their deathbed, they were doing these very interesting things, but we'll get to all of them. All right, so now that we are still going through the introduction here, remember we only talking about one guy. Gauss did come up with the Gauss-Jordan elimination, and then he also actually, you can see here, had Gaussian quadrature. So who has heard about something like that before? All right, no, okay, that's it. Well, I do think that some of you will encounter this if you go on to take more mathematics. It's usually something that I know that you hear about in calculus 3 or differential equations or some sort of advanced calculus classes, but it's just a simple formula to actually calculate essentially the curvature of the you can see there the quadratic graph. Hence why it's called quadrature. All right, and another thing, you guys aren't impressed. He came up with the equation to describe the normal distribution. So if you heard of the normal distribution, then that's what he came up with the equation for. He didn't actually come up with the idea of the normal distribution or the bell-shaped curve, but he came up with the equation to describe it. All right, so I think it's pretty obvious that anyone could draw a bell-shaped curve, but that the actual equation of that would be difficult to get because of the fact that it kind of takes a little bit of a turn right about here. And if you're taking calculus, you know that's sort of an inflection point. And so this isn't an easy function to come up with, but because of those inflection points, he was able to work those in there and came up with the equation for it. And because it's almost Halloween, I threw this one in here for you also. Now, if you want to have a nice Halloween costume and want to get a lot of attention, then this might do it. All right. Now, there are a lot of other areas of mathematics that you may not have heard about before. So you can see over on this side, you can see all these equations and these numbers and theoretical things. And so there's lots of types of mathematics that fall on that side, such as recreational math, like math that people do for fun. And actually somebody was just working this weekend again. I got another article today about a man who was working on the Riemann hypothesis again. And if you've ever heard about it, no one's ever going to prove it. And this guy claims he proved it. And all of a sudden over the weekend, like 80 mathematicians start telling him, your life work sucks and your proof is probably wrong, even though you put your whole life work into it. And so I don't know how that would make me feel, but that's why I don't really do a lot of this theoretical mathematics, because I don't want to spend my life doing that just to find out it was wrong, all in one weekend. And other areas of mathematics are history of mathematics, sort of like what we're talking about today, or logic, or set theory, model theory, proof theory. So if you take in any type of class that has a proof, usually the first one you'll see is proof by induction or something like that. And then even something like arithmetic falls in this category over here on the left, theoretical, adding, subtracting, multiplying, dividing, the foundations of all the other math, algebra, analysis, and combinatorics, geometry, topology. All of this falls over here, but there's a lot of interesting types of math that fall on the other side also, and you can see a lot of them. Game theory, or even probability statistics, numerical analysis, computer algebra, mechanics, operations research, mathematical programming. So anything more applied falls on that side. But there's a lot of interesting things over there. But if you want to work on sort of how will a calculator be programmed to do the math, then you're on that side. If you want to know why the math works, then you're on that side. And most mathematicians, especially in this book, if you read it, you'll find out are on one side or the other. Most people who do math don't jump from one side to the other. Either they're really applied and want to see how am I going to use the mathematics to make the world better or solve a problem, or they're doing the theory. So usually classes that people in college take in math are on this side of the spectrum, because you haven't really gotten to the point of actually going into a field of where you can actually apply the mathematics to a real world problem. So I was going to ask a question, but does anyone have any comments before we move on to the next little section of mathematics before the classical era. All right, so the next thing that we're going to talk about is really about those foundations and the arithmetic and adding and multiplying and dividing and subtracting before people had calculators, and people were actually doing everything mentally, and as the numbers get larger and larger, you can't really do the calculations mentally as easily, right? So this is an abacus, and the abacus, who has seen an abacus before? Right. Who has used one? All right, that's good. All right, no one here has used one. That's okay. But you might think that this was one of the first sort of counting machines or machines to help people do the mental math, but it really wasn't. There were lots of things that people used to try to help them not have to do the mental math before the abacus even came along, and this one was from the Inca. So who has seen something like this before? All right, so this is actually an interesting device, and it's, how do you say it? I looked up all the pronunciations because I really tend to say things incorrectly, but I think it's quick. But in either case, you can see that this was a very interesting device in terms of the fact that they had these strands here, and then they actually tied knots along it to indicate the ones place and the tens place and the hundreds place. Right. So the Inca people had a place value system, and so it's not really just like cavemen or people in caves making tally marks on the wall when you're thinking about how people are counting before calculators and all of that. They were actually trying to do something a little bit more creative and a little bit more useful at their time. So here is an abacus timeline. So the Inca population was doing all that before the first actual modern day abacus came into existence, and that would be the Salamis tablet in 300 BCE. And then I'll show you a picture of all of these, but the Roman hand abacus in 300 CE. So you can see already there was a 600-year difference here, and then down here, this, so in 1200, if you think about it, like that was only a little bit over 800 years ago. So I mean, that's really not that long ago that the Chinese came up with this, and then the numbers as we know them today, that they were created around that time, and then the Russians had a device in 1600, and then somewhere along the line, I know that you can't see it on the other side here, but in India, they were using these counting boards all the way up to, I think it's 1949 to do accounting in some of the offices in India. So the invention of the abacus spans quite a long time. I actually think this is an interesting part of history to get us up to where we have calculators like they are today. And believe me, I only picked the most interesting parts out of this book to talk about tonight because I know that the amount of time that we have is a little bit limited. But this is the Salamis tablet from the 300 BCE. I mean, all of these. So just sort of look at it and remember that this was actually just a slab of white marble. Right? So that's why it looks the way that it is, because it's literally a slab of white marble, and then they actually made marks on it to count things up. Right? So you don't really see all these things every day, but they are interesting. And then again, around this year, see, this is why I'm not ever going to take a history class ever again in my life. But yeah, but about 1,500 years later, the Chinese come up with the abacus as we know it today. And a lot of times, the abacus had, and I'll go back to the first picture, but the abacus actually was made from wood and metal, because the metal here, sort of, the Chinese thought that would serve as reinforcement so that the beads wouldn't fall off and it would have a little bit more strength to it. So there were a lot of things that were design features that the Chinese thought would put into some of the first abacus devices that they made. So keep that in mind also, that these were all very well-designed devices for the most part. So this one is actually one of the ones that was the Roman device that I mentioned. And if you look at this one, you can see that it's similar in nature, but these were just metal slabs because the Romans wanted people to be able to put this in their pocket and carry it around wherever they go. So if you think about how we carry around our phones with a calculator today, that's what the Romans actually wanted. They wanted people to be able to walk around with a calculator everywhere. Right? So they made these small enough to go in someone's pocket. Right? If you ask me, they were very, very smart and interesting people. And if you know about Roman numerals at all, I probably wouldn't want to do fractions with Roman numerals, but they had a whole system of fractions. But of course, that really didn't catch on because of how difficult it is to use Roman numerals sometimes to begin with. But you can see the Roman numerals here, X, C, 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 and all of the letters along there. So keep in mind that that's a similar device to what the Chinese had, that they wanted you to put in your pocket and take it along with. Right. Now, are there any questions? You guys don't look impressed, but I actually think that's pretty amazing. Actually, this is probably the most amazing one there is, because this is the one that I told you about that is from India, and sort of just remember that these types of counting boards were in use widespread up until 1949, and that's when the currency changed, and some of the counting boards became obsolete. Right. So think about if the United States ever changed all to the metric system, how many things would come to be obsolete? I mean, it's sort of like that. All of a sudden, all these big metal slabs are out of date and they get tossed away, and people have been discovering them and digging them up recently in the last 20, 30 years and whatnot. And so that's why we're seeing what some of them look like, because in 1949, that was still the tail end of them being used, and so that's before a lot of pictures of things started being taken, and so there's not a lot for us to see about these, but I do think that they're interesting, and you can see some of the stones are already in here. When I went to look for pictures of these, this one guy said he had over 200 of these in his home because he's just been digging them up, but that's nothing like what one guy has on the Windsor home. Did anyone see that TV story the other night? Does anyone know what the Windsor home is? You guys don't watch a lot of news, that's okay. But anyway, so the Windsor home actually is this mysterious noise in Windsor, and the Windsor residents don't know where it's coming from. It's been going on for like 6, 7 years, and this guy actually records the data what he hears 3 times a day, and so the news reporter came, and it was crazy. It's like one of those things that you see on CSI, and the guy has pin boards everywhere where the sound is coming from. And that's how I envision this guy, except that he has these counting boards all over his home instead. So I do think this is interesting. And here is the Russian version. And you can see the Russian version is a little bit different because the place values are by 1, 10, hundreds, thousands, and as you'll see in a moment, I think even on the next slide, you'll see that the Chinese version actually, on the top half, they had the 5, 50, 500, 5,000 instead, and then on the bottom half, they still had the 1, 10, 100, 1,000, 10,000, etc. But the Russians and the Chinese had very similar ideas about how to design this device, but they did the same thing that you'll hear a common theme about later on, that they didn't know about each other's inventions. So a lot of the things in math that you know of, like the Pythagorean theorem, Pythagoras wasn't actually the guy who came up with it, because more than one person was working on it at the same time. And then all of a sudden, out of nowhere, Pythagoras says, I'm the one, it should be named after me. So again, a lot of times, things like this happen. The Chinese swooped in. They said, we came up with this first, even though they really hadn't, as you can see. And that's why people attribute the abacus to the Chinese and not to any of these other groups. Right? So that's why it's called A Curious History of Mathematics, because there's a lot of fighting in here, a lot of people dying in this book, and actually there's a couple about people who claim to be wizards and sorcerers and things like that. So it's a very exciting read and very easy, actually. You don't actually have to know any math at all to read it, and still get a lot of excitement out of the story, and and appreciate all of the different turmoil that went on between all of these countries and all these mathematicians over the years. Okay. Are there any questions before we move on to the mathematics in ancient Greece? I thought this was interesting. So, does anyone happen to know who this is? And I will give a prize out if anyone happens to know, but
Is it Aristotle?
so close. It is actually Thales of Miletus. So it's so close. Aristotle, Thales, they sound just like, depending on how you say it, right? Tomato, tomato, Thales, Aristotle. All right, so one of the reasons why this guy probably does get confused as being Aristotle sometimes is Thales and Aristotle were both one of the 7 sages of Greece. All right, so that means that these are the 7 Greek philosophers that people would tend to have heard the most about, but Thales is one of the least known of all of them, and that's sort of why I picked him to sort of highlight out of the book today. So Thales is an interesting guy because he actually has a claim that he determined the height of the Great Pyramid using its shadow. So he went all the way from Greece out to Egypt, and try to figure out the height of the Great Pyramid. And the reason why he did that is because he was told as a young child that if he wanted to be a mathematician, all of the great mathematicians were in Egypt. So he believed his family and he moved to Egypt. He calculated the height of the pyramid because there was nothing else for him to do. And then eventually he moved back home, and then this happened. So I know that most of you have heard of the Pythagorean theorem, but I'm not going to tell you about the theorem, but what I am going to tell you about is the fact that the reason why Thales is important because he is the first one to actually write down any theorems. Right, so if you remember how I started this with the generalization that we had for the sum of the numbers 1 through 100, that generalization wouldn't have been done before Thales came around and said, all right, we're not just going to calculate the sum from 1 to 100, we're going to calculate the sum from 1 to whatever number we want and come up with a formula for it. And Thales was the guy who said, enough is enough. I'm tired of having to calculate things every time, prove things every time, so we're going to come up with these theorems. And Thales was the first one to put his foot down and say, I've had it with you angry Greek people who told me to get out of my own country and go to Egypt, and I'm coming up with this idea of proving theorems and writing down theorems. Okay, so and that's kind of interesting, right? Because I think you can think of a lot of times when you wouldn't want to have to reprove everything, but you would want to just have a formula to use, and so Thales made that possible. So here are some of the theorems that Thales was known for, the top 6 theorems. So he said that any circle is bisected by its diameter, or a circle is bisected by any diameter. So pretty much he said that if you draw the diameter of the circle, it's going to cut the circle in half no matter what circle it is. Right? So if you didn't have Thales proving that, then you would have to actually measure the circle every time and figure out for every single circle whether this actually cut the circle in half or not. So Thales was, in my mind, like a genius for writing down a lot of the stuff that seems like common sense, right? That if you draw a line halfway through the circle, it's going to cut it in half. Well, but people weren't sure that that would work for any circle until Thales came along. So you can give credit to him. Like, I mean, I wouldn't want to actually have to prove something like that. All right, another thing that Thales proved is that the 2 base angles of an isosceles triangle are equal. So what he proved is that the length of the 2 sides of the triangle are equal, then these 2 angles will also be equal. So again, that's common knowledge today, but Thales was smart enough to actually write it down, and now that's what we have is something that is, again, common knowledge. Then Thales also proved that when 2 straight lines intersect, the opposing angles are equal. So straight line from A to B and C to D, then angles 1 and 3 are equal, and 2 and 4 are equal. Now, if anyone hates geometry or hated geometry growing up, or having to do it in high school or whatever, then you can blame this guy for that also, because this is when the math teachers get crazy if they add 4 or 5 or 6 lines in there and say a lot of other angles are equal too. But for Thales, he just went as simple as possible. Right? He was a simple guy. Yeah. Thales also proved that the sides of similar triangles are proportional. So if the angles in 2 triangles are the same, then the ratio of, say, this side to this side would be equivalent to the ratio of that side to this side here. Now, again, that seems like common knowledge today, but it was not back in the time that Thales lived. So he really was the pioneer I don't want to say geometry because he really wasn't the pioneer of geometry. That was Euclid, but in his principles that you can read about. But if you ever take a class in that, please just memorize everything, because there's not any other way to do that, because these theorems are long, they're massive, and that's really the only way to get an understanding of these things, is by really memorizing the proofs and the steps, and then seeing how some of the steps can be used in other proofs. And that's what, again, Thales actually helped do. Another thing that Thales did is he said that two triangles are congruent if they have two angles in one side equal. So that is the angle side angle theorem, or ASA theorem, that is popular today. And there's side, which is sort of what we angle, side angle, all of those common acronyms for congruency of triangles and their angles and their sides all come from Thales. And then this one, I thought this is interesting. Thales said that an angle in a semicircle is a right angle. So actually, if you take half of the circle and you draw an angle in it, then it's going to be a right angle. And so that's pretty interesting. And you really don't even need the bottom half of the circle, because you just need to look at the semicircle at the top and see that if you draw an angle in there, then it will be a right angle. So Thales, he is very interesting in my book. Are there any questions about Thales, or does anyone have any comments about Thales? Or okay. Then we'll move on to another interesting man, and just like before, I'll sort of see if anyone knows who he is. So does anyone know who this man is? Does anyone want to give this one a shot? You give me his full name. Yeah, about that. Unbelievable. Yeah, so, Fra Luca Bartolomeo de Pacioli. Yeah, exactly. Yeah. And sometimes he's Paciolo. There's a lot of names for him, sort of because at the time, again, they weren't really writing things down, because he only lived from 1447 to 1517. And so what happened is sometimes names get misspelled and things. Actually, here, since you think I try, I'll just do a process. Because I can see how the name might be confusing, since they couldn't even write it down right back in the day. Right? So this guy actually is interesting, because most people wouldn't think of him as a mathematician, because he was really a friar. And so he went back and forth between doing church work and mathematics, and then he actually ended his life dying in the monastery and all of that. But in the meantime, he became the father of accounting. So he lived a pretty interesting life, and he actually came up with the system of double bookkeeping that I'll talk about in a moment. But this was a picture of his first book. And so this was called the Summary, I'm going to say it in English, Summary of Arithmetic, Geometry, Proportions, and Proportionality. And it was first actually published in 1494. So since he was born in 1447, you can see that, you know, this guy was sort of older than some of the mathematicians that we'll talk about. because some of them will, one of the guys died in his 30s, and a lot of the things you'll realize, hey, they didn't have this health care back then, or people were throwing ice water on them and things like that caused them to die at an early age. So on this double entry accounting method that actually was described in the book here is now known as the Venetian method, if you've heard of that. Does anyone in here know anything about accounting? I mean, I took a couple of accounting classes myself, and then I was in the national accounting competitions when I was part of the Business Professionals of America, and then I went to the national competition that year in accounting and actually lost in the first round because I couldn't spell the word lexicon and give its definition. And does anyone know what a lexicon is? That's not even about accounting anyway. The lexicon is just really a dictionary. So it's a dictionary of all of the words or the terms or whatever. And so in the world of accounting, it's a dictionary or a book of all of the words or methods relating to accounting. So again, this guy, one of the first to come up with these ideas of accounting. All right, so now another interesting thing about the Summa of this book here is that it was one of the first books to be printed on the Gutenberg press. So the 1400s, this is brand new, and if you read the book, they're talking about how all of the books that people had were being verbally translated from the foreign language that they were in into Latin, and then they were being printed in Latin on the Gutenberg press. So this guy was super important in Italy at the time because his book was actually being printed, and it was translated and printed and written down. So this was, again, a very interesting thing because books really weren't actually written down at the time, or printed, to say the least. So this is sort of the trial balance or the double bookkeeping method that I told you about earlier that the friar came up with. And so pretty much he said that if you put all of your debits in here, or your debts for the year in one column and your credits on the other column, then if the amount of debits or your debts equal the amount of credits, then your book is balanced. Otherwise, you made a mistake, or you're a liar and a thief. But of course, he would say that because he's a friar, right? So he doesn't want people lying or cheating or any of that because he's associated with the church. But who has seen bookkeeping like this before? I mean, this is actually a pretty nice way to do bookkeeping, keeping the debits column separate from the credits column. And so that makes it a little bit easier for people to read. And I've worked in a lot of situations where the credits are actually more than the debits, which actually is good when you have a little extra money coming in. But then, of course, being a friar, he said, if that happens, then you should give back to the people. Give back to the church, give back to the friars. I don't know what he wanted. Maybe he wanted a nicer bed rather than the cot he was just sleeping on, but who knows? The friar said, though, that the book should be balanced every time. All right. So, now, around the time the Summa, the friar's book, was actually published, he actually was actually invited to be friends and colleagues with this man right here. Okay, who is it? Leonardo. It is. Very good. Da Vinci. And so he was actually invited to teach math at the court of Duke Sforza in Milan. So all of a sudden, this guy is going to Milan, and he is helping out Da Vinci, and this is Duke Sforza. Now, by the way, not much is known about this Duke because everyone after him who came in his place is also named Duke Sforza. So there's like 8 of them, and people don't know which one is which, but this happens to be the right one. I do know that, but I don't know much about this actual guy because all of them are named Duke Sforza. But anyway, the Duke invited the friar and Da Vinci to come to his school, and the friar was teaching math, and then Da Vinci was his student in math, and that's when the friar was writing another book called Of Divine Proportions, and that wasn't published until 1509, but the friar wanted the book to have illustrations in it. So he hired Da Vinci, and then he was too cheap to pay Da Vinci for his illustrations, or else he just couldn't afford to because he worked for a church and all of that. But in turn, he helped Da Vinci with his proportions, and that's why to this day, the Last Supper here is known as one of the paintings that everything is proportional in, and that because the friar helped Da Vinci with the proportions to make everything exactly the way that you would see it in this painting. All right. Which I wouldn't have known that Da Vinci had help from an actual mathematician, because it doesn't seem like a likely thing to happen, right? So, but that's exactly what happened. And then the friar also helped Da Vinci on a couple of other things, such as he calculated the amount of bronze needed for all of Da Vinci's statues, like this one. And actually, I think if I recall, this is actually the statue of Duke Sforza. Right? So, but Da Vinci has a lot of statues that he is famous for, but this happens to be one of them. So if you ever wanted to calculate the amount of bronze or something needed to make a statue, of course you need a lot of math in order to be able to do that. Right. Does anyone have any comments about that? We have like two more big people to talk about in the journey through this book, but that is it for that last section here. This one is about the Renaissance and the Revolution. So does anyone happen to know who this guy is?
Pascal.
Yeah, do you know his first name? Okay. Well, here, I'll give you a prize then just for knowing it was Pascal. Nice try. All right, so yeah, this is Blaise Pascal, and any guy whose first name is Blaise and last name is Pascal probably is a pretty cool guy. His clothing wasn't the best, but it was the 1600s, so what can you do? And this guy was only alive from 1623 to 1662. All right, so not a long time, because again, he was one of the people who died of the pancreatic cancer. All right, but again, very interesting guy. All right, so one of the things that Pascal is known for is his Pascal's triangle. Now, what you need to remember, though, is, like I mentioned about Pythagoras, he wasn't the first to come up with the Pythagorean theorem, he took credit for it. Pascal was not the first to have discovered this triangle. All right, now, keep this in mind, Pascal did not actually publish his triangle until 1655. So, now, if I go back in time from 1655, then all the way back to 953, all right, the El-Kharaji Persian guy, He's pretty famous for other things, but he actually knew of the triangle between about 1000, right, somewhere between when he was born in 953 to 1029. And you can see that Al-Khwarizmi had a triangle in his work here, right? And his wasn't actually in the same direction, but you can see the ones along the outside and so on. So when we go back and you see the ones along the outside that I'm talking about. Right, so Al-Khwarizmi knew about it, like 600 years before Pascal. Even though I like the dude, he stole someone else's idea. All right, so what would the friar have to say about that? You have to wonder. But if you haven't seen this triangle, who has seen this triangle? Right, a lot of them. You can see how it's constructed. 1 plus 1 is 2, then 2 plus 1 is 3, 2 plus 1 is 3, 3 plus 1 is 4, 3 plus 3 is 6. So each number in the triangle is the sum of the 2 digits directly above it. All right, so we'll keep that in mind. But does anyone happen to know who this guy is? Oh yeah, this one's done. Yeah, this is. Yeah, this is Omar Khayyam, and he was from Iran and a Persian mathematician, astronomer, and poet. So he actually came up with a version of the triangle as well, but let's see, I had the year, but I had it on a different page. Said I am not keep any track of all of these dates, but oh, it's somewhere. I'll tell you the date in a moment. Yeah, but I will say that not much is known about his version of the triangle and what it looked like. That all got sort of lost. However, in the 1200s, Yang Hui actually came up with the triangle in China. So you can see his version, and this is 1, 1, 1, 1, 1, 1, 1. One's all on the outside, right? So remember that Pascal still didn't come along until the 1600s. So this guy is working in the 1200s, still 400 years before Pascal. So Pascal, stole from Iran. He stole from China. This Pascal is not a pleasant guy. Maybe he deserved his untimely death. Maybe he did not. Who am I to say? Does anyone know who this is? Nice try. Yeah. This is Tartar. Oh yeah, well there's Tartar jellies. Yeah, tartar jelly. And so, has anyone heard of tartar jelly? So he also created a version of the triangle, but he lived from 1500 to 1577, so still about 100 to 200 years before Pascal came around. All right, so keep that in mind that Pascal's triangle, as we know it today, really was not invented by Pascal. All of these guys before him actually came up with the idea of the triangle, and I will say though, it is a useful triangle. So I'm going to show you some of the things about it that you may or may not have known already. One of the common ones is that it's a table of the binomial coefficients. So who has seen this before as a way to expand binomials? All right, 2 people. The rest of you, that's okay. All right, so that's one thing that the triangle can be used for. there are some hidden sequences in the triangle. So you can see that I put all the numbers to the left here so that you can see them a little bit easier. But the first column here is just the natural numbers, 1, 2, 3, 4, 5, 6. All right. The second column is the triangular numbers. So that's the 1, 3, 6, 10, 15. And triangular numbers, if you haven't heard of them, are just the number of dots it takes to make various size triangles. All right, so you can look that up, but it's pretty interesting, actually. And then the fourth column are the pyramidal numbers, so 1, 4, 10, 20. And then you can see that that pattern would continue if you start it in the next column, and the next column, and the next column. All right, but yeah, that's only if you're interested in geometry and drawing up the triangles and the dots and all that. The triangle can be used to find the powers of 2 easily if you add up the numbers in each of the rows. So the second row 2, third row 4, fourth row 8, and then so on. And if you want 2 to the 100th power, just write out enough rows of the triangle and you can add up the numbers, and that's probably easier than multiplying 2 times 2 times 2 100 times, depending on what day of the week it is. All right. Here's another interesting one that people don't actually know. So you see how here you're adding the numbers to get the powers of 2? Right? If you just put the numbers together, then you get the powers of 11. Not multiplying, but actually putting them together. Then 121 is 11 to the second, 1,331 is 11 to the third, and 14,641 is 11 to the fourth. So if you want to surprise people at a party and say, actually just go to the bar after this and say, hey, if I can do 11 to the 7th mentally, will you buy me a drink? You'll carry the triangle in your pocket. You know, remember the Romans said to carry the abacus in your pocket, carry one of these triangles in your pocket quickly and just bring it out, and then now you know what 11 to the 7th is. Or get a Pascal's triangle tattoo on your arm. Both of those are a good option because it makes for a good party game when you can do 11 to the 7th pretty quickly. Oh yeah, I mean, I've done that before. It's impressive. Now, there also is a hockey stick pattern here. So all you have to do is, if you start at the 1, bordering one of the sides of the triangle and then go down like this, then the sum of all of these numbers will equal that number. All right, and the sum of all of these numbers will equal that number. The sum of these numbers will equal that number. So that pattern can be seen all over here. 1 plus 4 is 5. All right. Or 1 plus 3 plus 6 is 10. So that's an interesting pattern in the Pascal's triangle also. Yeah, I mean, that's interesting. That's a triangle for sure, right? The Fibonacci numbers are in the triangle. Who has heard of the Fibonacci numbers? Yeah, Fibonacci himself is an interesting guy. Like, if I feel like I'm cutting any of these people short on what they did, I really am, because a lot of these guys have a lot more stuff that they did that I'm not telling you about. But if you look at these diagonals and add them up, you get the Fibonacci numbers. Right? 1, 1, 2, 3, 5, 8, 13. Right? So that's an interesting tidbit. Right, now, let's see. You can find the prime numbers from Pascal's triangles. Let's see, where is it? I had the example written down. Row 7. Row 7. Where is row 7? All right. So if you look at row 7 here, right? You see how 7 is a prime number, then that means that 7 will be divisible by all the numbers in the row. So 7 goes evenly into 21 and 35. So again, since actually 3 is a prime number, right? 3 goes evenly into 3. 5 is a prime number. 5 goes evenly into 10. So you see for numbers that are not prime like 6, that doesn't work. Like 6 doesn't go into 15. So if the number is prime, then it will go into all the numbers in the row. All right. So that's how people were able to find some of the prime numbers so quickly, is that they wrote out a ton of rows of Pascal's triangle and then tested the divisibility in each of the rows. Right, there's quicker ways to do it today, but the last prime number, I think, took 213 days to find, but they're up to a really large number of prime numbers. But prime number theory is another thing that's talked about in this book. Interesting. I would highly recommend it. 10 out of 10. The perfect squares here. If, say, you want to know what 4 squared is, you look right to the right, and 6 plus 10 is 16, and that's 4 squared. You want to know 3 squared, here's 3. Look to the right, 3 plus 6 is 9, which is 3 squared. Right, so if you want to know, what 144 squared is, just write out enough rows of the triangle, and then look at the 2 numbers to the right of it and add those 2 numbers together. And that's still easier, probably, than let's say x plus y to the 144th power, right? All right. So there are some other interesting properties in the triangle. The points on a circle. So if you have 1 point on a circle, then you can make no segments in the circle. But if you have 2 points on the circle, you can make 1 segment. 3 points on the circle, 1, 2, 3. You can make 1, 2, 3 segments, but 1 triangle. And if you go on from the number of points, segments, triangles, quadrilaterals, pentagons, and hexagons, and septagons, and so on, then all of those will form Pascal's triangle also. All right, so I find that to be a fascinating thing here. And then lastly, if you actually take all of the odd numbers in Pascal's triangle and you actually fill them in, say, black, in the even numbers white, then you end up getting a cool design, and they call that Sierpinski's triangle. Who has heard of Sierpinski's triangle before? Isn't that interesting? Sierpinski's triangle is pretty interesting, but again, it all comes from Pascal and his triangle that he claimed is his, even though it really isn't. Now what do you think about the guy? Yeah, I mean, for coming up with a triangle that has so many patterns in it, I do think that he is somewhat of a cool guy. All right, so, oh, by the way, I am done talking about Pascal's triangle, but if you really thought he was cool, he did do a couple of other things. He came up with Pascal's theorem, which is actually diagrammed here, that just says that 6 arbitrary points are chosen on some sort of conic, and in this case it's an ellipse. So you have the points A, B, C, F, E, D, so the 6 points on the outside. Then if you actually join all of those points by line segments, which you can see, all of these actually are joined with line segments A to B, A to F, and so on. Then, then these 3 points where all of these segments intersect will always form a straight line. So you can see that this is a straight line going through G and K. So that means essentially that he knows, or he proved, that H isn't going to be over here, So it goes G, H, and then back to K. Right? He knew that these 3 points would all, these intersection points here, here, here would be all on a straight line. So he proved that. A very interesting guy, and they actually call that the Pascal line of the hexagon or the conic or whatever shape you're doing this with. Actually, you could do this with any shape, but it's most commonly done with the ellipse or the circle or something like that. All right, now here is where things actually get even more interesting with Pascal. He actually invented probability theory with another guy. Does anyone know who that guy is? Don't guess at all. Well, that's okay, because I'm going to tell you this was Pierre de Fermat. And actually, we're going to have a film later on, I think it began in November, about this guy and just his famous theorem and his life. He's an interesting guy in himself. But he actually, with Pascal, created probability theory based off of his triangle. All right, so then, does anyone know who this guy? Actually, it's this guy. This is an easy one. You don't know this one. Yeah, this one is Newton. And why is he interesting, or what is Pascal's actual connection to Newton? It's that Pascal actually created calculus a decade before Newton did. And so Newton actually stole Pascal's work, which is interesting because Pascal has stolen somebody else's work. All right, it's just that Pascal waited 600 years to do it. Newton only 10 years. All right, so Pascal was, pretty much still around when Newton was stealing his work. So maybe, that had something to do with his untimely death. You never know, because you don't just all of a sudden die with something with the pancreas unless somebody gives you something you're not supposed to have, and it may have been Newton, but we'll never know. But yeah, you could read the book to find out. And then here is another thing that is interesting, because if you remember what I said, the abacus was created because people didn't want to do mental math, right? So Pascal didn't care that the abacus was already there. He actually created a device of his own because he didn't like the abacus. And so this is what he called the Pascaline. So he named it after himself, the Pascaline. And it actually was a pretty crappy machine, because if you actually turn one of the wheels, the rest of them would fall off. All right, so he didn't really put as much craftsmanship into it as the Chinese did. That's why I made a big point to say that the Chinese had the metal and the wood, and they crafted it nicely, because Pascal's invention fell apart if you even touched it. Right, so smart guy, he created this triangle. He came up with calculus. He came up with probability theory, but he could not create something better than the abacus. He tried. He also came up with Pascal's law. Who has heard of that one? Yeah, and that's a pretty interesting law. I mean, you can see it diagrammed here. Pressure applied on one point of liquid transmits equally in all directions. So if you really want to get the anger out, just try out Pascal's law one day. Just be a little bit careful. And then finally, one thing about Pascal that I did not say before is that he actually did design a public transportation system for Paris just before dying of his pancreatic cancer. And he was only 39 when he died. So if you actually know anything about buses, does anyone know anything about buses? Yeah, the whole thing about buses is that is that this really was the first bus system. Right? Pascal came up with these horse-drawn bus systems, and actually, because he died, it only lasted 15 years, because what happened is what happens in government today, right? Because Pascal had died, the French government actually raised the bus fares, and people couldn't afford to take the horse-drawn buses anymore. And so the bus system died, right? That's the same thing that happens in government today, politics, whatever. And so just like over in France, back in the days, the 1800s here, or actually, not the 1800s, I forgot, the 1600s. Back in the 1600s, it was over. So then that was in the 1600s. It's lasted 15 years. And then the next bus system actually to be known anywhere after this wasn't until the 1800s. So this is Pascal, like, for having a horse-drawn bus system. You see, like, why I think he was a pretty cool guy, because he came up with this before anyone else. Like, it's sort of like Blockbuster. Right? They had an idea for a version of what we would call Netflix today, but it failed because the infrastructure wasn't there to support it at the time. And so now we have Netflix, but it was really Blockbuster's idea. Right? So the bus systems today were really Pascal's idea back from the 1600s. So I like the guy. And by the way, this wasn't just like a one-line system. He had 7 bus lines, so 7 lines of horse-drawn buses. Right? So this wasn't like something that would have been very easy to do. You had to have the dirt road set up and everything. So, okay. Last time. So into the modern era today. So this is John von Neumann, and he was one of the guys who actually came up with game theory. So who has heard of game theory? Right, 2 people. So if you're not familiar with game theory, it has a lot of applications in modern day, like stocks and bonds and mutual funds, and seeing which one would pay off the most. And so you can see here that sometimes that's what you have to do, right? And you see that although stocks have the the client number right now, they're overall the best right now. Right? So even though you're getting minus 13 in some of the stocks, it's growing at the best rate. So that's what you invest in, even though some of the stocks happen to be going down at the time. So there is also the prisoner's dilemma. And who has heard of the prisoner's dilemma? Right, essentially, okay, so to summarize then, so you can hear of it before, it just says if there are 2 people who are accused of a crime, and one of them cooperates with the police and admits to the crime, and then if one of them defects and does not commit to the crime, then here is what happens. So person A cooperates and person B cooperates, then they both serve 1 year in prison. But if person A actually says, oh, I'm betraying person B and saying that person B did it, then actually person B served 3 years, and you can see what happens. If they both betray each other and they say, you did it, then they both have to serve 2 years. Now, if you look at it, there's only one situation that is a good situation. It's actually if they both stay silent and they both serve 1 year, right? But it would be better then, because you don't know what the other person is going to do, then you just admit to the crime and hope for this. Right? So you're hoping in your mind that both people would admit, and then and then you both serve 2 years and then not risk reaching the maximum of 3 years, right? So you can read a lot more about the prisoner's dilemma. I actually had to use that today when somebody was talking about something to do with politics in the news recently. I actually said, well, it's in my best interest not to actually do this because of the prisoner's dilemma. And so what I said was backed up by math. Right? And then the person shut up. So, okay. And does anyone know who this guy is? Yeah, John Nash. So he is of A Beautiful Mind fame. You've probably seen his movie, famous mathematician. So the interesting thing, though, I do have it written down here, but does anyone know how he died, by the way? I mean, that's a pretty interesting way to die. He just died while riding in a taxi in New Jersey, which I would never go to New Jersey because the Jersey Shore and all the other stuff. I don't like that comes out of Jersey. But I can get Jersey Mike's up right down the street without having to go all the way to Jersey. So I probably have no reason to go there now. But in either case, that's how John Nash died, is on the Jersey Turnpike. So after such an interesting life, that's how he died. But again, this book is full of people dying. Right? So if you want to hear about that type of stuff and all the mathematicians who end up in the wrong place, read the book. Right, so here's another thing that John Newman's game theory can be used for, and it's to analyze modern day sports like baseball. So here's the statistic that Major League Baseball game theory analysts came up with, that if pitchers threw 10% fewer fastballs, then they would concede 15 fewer runs per season. And the calculation was done, and that would mean that the team would win about 2 more games per year. All right, so think about that. If you have 5 pitchers in your starting rotation, each of them throws 10% fewer fastballs, 2 games times 5 pitchers, they win 10 more games. You never know what that would do. Okay, so that's something to think about. So tell that to the Detroit Tigers. They're still going to suck next year no matter what, but you can try to pass that piece of advice along to them. And for the NFL, if you use game theory, if a team went from passing 56% of the time to 70% of the time, they would score an additional 10 points per season. So think about that. They say from the calculations, on average, that would mean each team would get about 3% more points per season. So well, that doesn't seem like a lot, especially when you're the Lions and you lose by 40 or 50 points, all right? So, but maybe the 10 points make it seem like it's not a blowout. And you can come back from Dallas with some dignity, all right? Are there any questions about that? I actually do think that a lot of this game theory stuff as it relates to sports and things like that is interesting, and that's why a lot of the different sports, major league sports these days are coming up with their own game theory departments, not just the statisticians like in the past, but an entire game theory department just based on simulating games, saying what happens if the other team did this, and that's how we come up with this information. All right, well, that is it. So does anyone have any questions or comments? All right, some people are already leaving, so I guess that means that we reached our end.
How much is that book?
Oh, let's see. You can check them out from the library for free here, but I think that if I remember I got mine, $20 maybe.
It's 15.
Yeah, how much?
15.
Yeah, that's why I thought 20 is the most I paid, but I mean, I would still check it out in the library before you decide if you want to buy it, but I still think that it's interesting because it is relatable. You know, that's why I liked it. So, all right, well, thank you very much. Make sure that you get your extra credit slips, or if you're in one of my classes, turn in your survey before you go, so that I know that you are getting the extra special credit for being here at the right time. And also, if you need the MMI credit to sign in at the front, please, that will help also. All right. The sign-in sheets go over there. Everything else I can probably take over here depending on the situation. So, yeah.